Hello, I'm Sardeep and this is my linear algebra teaching video on Markov chains. This is topic 5.9 from our textbook. So Markov chains essentially talk about probability, where probability isn't fixed, but it depends on the present state. And we'll actually talk about what is a state, what is an event, all of this. And Markov chains are interesting because they have a lot of applications with linear algebra, which we'll also go into later. And today I'll be walking through this with the very famous example of flipping a coin. So before I talk about Markov chains, let's talk about coin tossing, right? So when you flip a coin, you can either get heads or tails, right? And we'll take two different cases today. So first we'll take the case of a normal coin, right? And for a normal coin, if I'm flipping it through like a simulation of coin tosses, I have two different outcomes, right? I can get heads or tails. And when we talk about probability, these different outcomes are called events. So I'll write down my two events, which are heads and tails. And what I know is that if I flip a coin, the probability of getting either event is 0.5. So probability of getting heads is 0.5, and the probability of getting tails is also 0.5. The probability is fixed, so it doesn't change. Say I'm flipping a coin 20 times, right, like a normal coin, and on my 18th toss, I've somehow gotten all heads so far. This doesn't mean that, oh, because I've gotten so many heads, I'm going to get tails on the next iteration or the next state. This probability is fixed. But what if the probability wasn't fixed? Like, what if the coin was magical or rigged, right? So let's take an example of a rigged coin, which works magically, right? We'll say our rigged coin still has two events that can happen, which is heads or tails. But let's add some rules for the rigged coin. So say that we have heads now. The probability that given we have heads now, the next event will also be heads, which means that the state is unchanged, is going to be 0.7. So this means that given that we have heads now, the probability that the state changes to tails is 0.3. For tails, say that we have tails now. The probability that the state remains unchanged at tails is 0.6, and then that means that the probability that the state changes from tails to heads is 0.4. So these are the rules of our game. And in our game is just a simulation of coin tosses, right? So say I have a little table over here and I'm flipping my coin, right? My rigged coin. And say I deliberately put down the coin at heads, right? This somehow counts as a flip, I guess. And my current state is 100% heads and 0% tails, right? So we'll write vectors x, which represents the fraction of the number of times we've gotten heads and tails, as so, where h plus t will be equal to 1, because in probability theory, when we add, in probability in general, when we add up all the different events that can occur, the likelihood of the different events, they should add up to 100%, which represents all the possibilities. So for a coin, we can say that the initial state, which is x naught, is 1, 0. And this is because we have had one toss so far, and we have 100% of the tosses as heads and 0% of the tosses as tails. This vector has real positive numbers, and it represents 100% of the possibilities. So we call this a probability vector formally. So let's define a probability vector, right? So in probability, obviously the probability of something can't be negative, right? It's always going to be 0 or it's going to be some real number between 0 and 1, right? So we say that a probability vector is a vector with non-negative entries summing to 1. Okay. So next, let's organize the rules of our rigged coin into a matrix, right? So for this, we'll write two vectors for the heads and the tails, right? We'll say the heads vector is going to be equal to 0.7 and 0.3 because this represents all the combinations given we have heads right now. And for the tails vector, we'll write this as 0.4 and 0.6. Remember, it's always important to keep the same notation where we have heads first and then tails, which we're also denoting over here. So both of these are probability vectors. So we'll call the rule matrix P. And our rule matrix will essentially have heads and tails. Our heads vector and tails vector, which is 0.7, 0.3, 0.4, and 0.6. So this vector is actually called a stochastic matrix. So a stochastic matrix is a square matrix where the columns are actually probability vectors. So as we can see here, these are probability vectors because if we add these up, we get 1. We add these up, we get 1. More formally, this is called a column stochastic matrix, but we'll just call this a stochastic matrix for now. Okay, so let's formally define a stochastic matrix. And this is just a square matrix as probability vectors. Okay, so yeah, we've already checked the columns. It's a probability vector. So now let's combine these two ideas of a probability vector and a stochastic matrix. So like I said, our game is a simulation, and our initial toss, which we'll call our initial state actually, is 1, 0, right? So as we keep flipping the coin and we keep getting more simulations, we have basically a rule matrix which moves us through time, and we have a starting state. So this is like a chain of events, and we actually call this is actually a chain called a Markov chain in math. So let's define what a Markov chain is. So a Markov chain is just a sequence of these probability vectors, right? x0, x1, x2, all the way up to some, like for us, x is 20, but it can go on for as long as you want, where you have, all right, let's just write this down. x2, so on, where x naught is given, but x1 is actually p, which is a stochastic matrix or rule matrix times x naught. From this, we get x2 is p times x1, and this sequence continues, right? We can actually write this as a first order difference equation where x of k plus 1, let me write that over here, x of k plus 1 is just p of x, p times x of k, where k is some integer, some real integer. Positive. Actually, not positive because you can have 0. Yeah. So now let's actually play our game, right? So we know that x naught is going to be equal to 1, 0, but what happens on the next toss, right? So let's apply a rule. x1 is just going to be equal to p times x naught, which is 0.7, 0.3, 0.4, 0.6, times 1, 0, which is equal to 0.7 and 0.3. So for the second toss, this is just p times x1, which is, once again, 0.7, 0.3, 0.4, 0.6, times x1, which is 0.7, 0.3, and this is going to be equal to 0.61 and 0.39. You can do the math if you'd like to verify. And what does this mean, right? This means that after 2 tosses, there's a 61% chance of heads. And if we keep doing this, actually the vectors won't change anymore. And they'll reach some equilibrium called a steady state, and we call this vector our steady state vector, right? And this happens because of an important theorem. So let's talk about this theorem. This theorem tells us that if we're given a P, if we're given a stochastic matrix P, right, then it must have an eigenvalue of 1. Some eigenvalue which is 1. So let's do a quick proof of this. And why is this true, right? Proof over here. Because P is column stochastic, we can say that the sum from I equals 1 to n of P sub ij is equal to 1 for every j, right? And this is the idea of a column stochastic matrix where like we said, each of the columns add up to 1, and because they're probability vectors. So let's write this out. P sub ij is just an element of the matrix. So now let's write the vector 1, which you'll see why we're doing. So you just say 1 is a vector, right, of just 1s. So we set up a vector of all 1s, and the jth what we know is that the jth component of P transpose times the 1 vector is equal to the sum from I equals 1 to n of P sub ij, which we just established equals 1. So let's write this out. P transpose times the vector 1 j is equal to the sum I equals 1 to n of P sub ij. Let me write that cleaner. 1. So P transpose times the 1 vector is equal to 1 times the 1 vector. And this means that 1 is an eigenvalue of P transpose. But we know that a square matrix and its transpose have the same eigenvalues, right? So hence we know that P must have lambda equals 1. So because 1 is an eigenvalue, we're simply looking for its eigenvector. And this means that there is a vector q. When we multiply by P, we just get q. So we can write this out, q. What does this mean, right? Its significance is that eventually we take a vector and multiply it by a rule matrix, but it doesn't change, right? And this represents steady state, like I said earlier. So this is our equilibrium, where if we keep playing the game, this won't change, right? So what is our vector q in this case, right? We get 0.7, 0.3, 0.4, 0.6, q is equal to q, right? So to simply solve this, we can just look for the null space of P minus the identity matrix, which we get from this P minus the identity matrix times q equals 0, right? So let's actually calculate this out really quickly. We get 0.7, 0.4, 0.3, 0.6 minus the identity matrix gives us negative 0.3, 0.4, 0.3. Okay, this is also just negative 0.4. Right? And we can basically just row reduce this matrix over here where we have like 0.3, 0.4, 0.3, and negative 0.4. And to row reduce it, we simply just multiply this row by negative 1, and we add the first row to the second row, right? So we get negative 0.3, 0.4, and we get a 0 row over here. So to simply solve, and we can basically just like make our lives easier, and we can say this is negative 3, 4, and this is 0. So this is our null space of the matrix, and basically we have a pivot here. So this tells us that x2, which is the variable corresponding to the second column, is going to be free. So we can simply say that, actually, we'll call this q2 because we're just dealing with the variable q. So we can say that the q is just equal to q1 times q2, and this is just going to be q2, and we know that negative 3q1 plus 4q2 equals 0, so we get that q1 is just 4/3 of q2. And this gives us a basis for the null space of 4/3 1, and we can just write this basis as we just write this as 4 3. So we want q to essentially be a probability vector, right? So this is not a probability vector, but we can actually normalize it like we did earlier with vectors. So we can normalize this by dividing each component of the vector by its sum, and then we can get a probability vector of 4/7 and 3/7, which is just 0.571 and 0.429. This tells us that, okay, so we have this, and this just tells us that after a lot of simulations, right, if you flip the coin long enough, the probability settles exactly this vector. So we have 57.1% heads and 42.9% tails, right? And this won't change. So that's essentially how a Markov chain works. This is actually called a dynamical system, fun fact, where the probability changes over time and it's sort of random, right? But we can still predict the end behavior of what happens to the system. And funny enough, this doesn't depend on the initial state, but yeah, this is how you use linear algebra to work through a Markov chain. Thank you.